started studying RLI starts indeed. So I studied on his fundamental papers on the delta S metallicity indicator and continued to follow his relevant contribution to RLI studies in the literature. And I will talk of some results based on modeling of RLI stars as standard candles and stellar population tracers. It has already discussed yesterday and mentioned in the previous talk that RLI are low mass fundamental population tracers. Indeed, they are central helium burning low mass stars in the horizontal branch phase. They are the most abundant class of pulsating stars in the Milky Way, so their characteristic variability allows us to use them as standard candles in galactic globular clusters in the bulge, but also in the nearby galaxies, as we know. And they also represent a valuable alternative to classical Cepheids in the calibration of the local group distance scale, if we want to rely on a completely population to route to the cosmic distance scale. But obviously their properties are traditionally used to I'm not able to go on. I don't know why. There is something I blocked. Okay. And so they are excellent tracers of chemical and dynamical properties of all stellar populations. Indeed, they can be used to probe the properties of all stellar populations in many respects. Indeed, they are used to derive distances, so in principle also to derive the 3D structure of the host stellar system. Their characteristic properties with respect to the Bailey diagram distribution, but also the Ostrov behavior, can be related to arguments on the formation of the galactic halo. We know that RLI properties depend on the metal abundance, so they can be used to infer information on the metallicity distribution. They also depend, the pulsation properties also depend on the helium abundance. So if these distances and metallicities are known, we can use the observed pulsation properties to constrain the helium abundance, so possible helium enhancement, enrichment. This is correlated, for example, to the discussion on multiple stellar population in globular clusters. And finally, we know that it is true that masses can be measured, as stated yesterday, only if RLI belong to binary systems, but indirectly we can derive masses from the behavior of pulsators, double mode pulsators in the Petersen diagram, representing the period ratio as a function of the fundamental period. We also know that a theoretical analysis is important to understand the dependence of the properties of RLI on different input parameters, so to better understand how to use these variables as tracers of stellar populations. And I would like to recall this fundamental paper by Van Albade and Baker that nicely represented maybe for the first time the clear link, even if this relation descends on the basic period mean density relation of a pulsator. These were derived on the basis of an extensive set of linear non-adiabatic hydrodynamical models, and indeed they represented a clear link that can be established between pulsation parameters and evolutionary ones that in turn are function of age and chemical composition. We know that in order to predict all the pulsation observables, linear models are useful, but do not provide the full amplitude behavior. And you also need to include convection in the models in order to reproduce the red boundary with instability strip that is related to the interplay, to the interaction between pulsation and convection. So nonlinear convective models are needed. And in the last decades, there have been a lot of efforts to produce both updated linear models and nonlinear convective models. These are some of the authors that included convection in their nonlinear hydrocodes. And in the following slides, we present some of the latest results that have been obtained by myself in collaboration with Giuseppe and other co-workers, based on Stellingwer's code that have been then updated and adapted to different classes of pulsating stars. But I started working with Stellingwer's code on the basis of RR-Lyre models. And the latest model compilation, we presented models for different metal abundances, covering a wide range of abundances, masses that were taken from the evolutionary scenario by Pietrinferni et al. So basically the Basti stellar evolution database. Two masses and 3 luminosity levels were indeed taken into account to model possible evolution of ZAB. And we also extended these models to higher helium abundances in order to possibly model some peculiar properties of RR-Lyre that are observed, for example, in some bulge globular clusters such as 6441 or 6388. Here is a plot showing the location of the predicted instability strip for a number of the selected chemical composition. So you see that the helium abundance increases from left to right, whereas the metallicity increases from top to bottom. And you see the predicted instability strip boundaries. These are the extreme boundaries. So the red line is the red boundary of the fundamental bond. The blue line is the blue boundary of the first overtone mode, compared with evolutionary tracks in the Basti database. And so it is interesting to see how the instability strip is populated by different masses and different evolutionary stage according to the selected chemical composition. The computed models produced a wide and extended atlas of bolometric light curves, and it was interesting to study the dependence on both metallicity and helium abundance. So here you see again the metallicity increases now from left to right, and the helium abundance is represented by the 3 colors in each panel. So we see that the morphology at fixed temperature is not particularly dependent on the helium abundance, apart from the fact that as the helium abundance increases, the zero-age horizontal branch luminosity increases, so you have brighter models, and if it increases up to 0.3, you can have also lower amplitudes. We also converted the bolometric light curves into a variety of photometric filters, so we were able to derive a mean magnitude and colors, and in turn to compute different kind of periluminosity color relations, and also the reddening-free period-wise and night relation that I recall our relation where the magnitude is replaced by a magnitude minus a color term, whose coefficient is exactly the ratio between the total and the selective extinction. So they are reddening free by construction, even if you have to rely on an extinction law, obviously. And these are the period-wise and night relation in the Johnson-Coulson filter for different combination of bands, even 3 bands in the right panel. And you see that there is a combination that is for the selection of B minus V magnitude B minus V color, for which the predicted Wassenaar relation is essentially insensitive to metallicity. So this is particularly useful to derive individual distances of RR-Lyre, even if you do not know accurately the reddening and the metallicity. These are instead the predicted periluminosity relation. Different colors represent different metal abundances, with the faintest relation corresponding to the most metal-rich models and the brightest relation corresponding to the most metal-poor ones. In the left panels of both figures, you have fundamental and first overtone relation, whereas in the right panels, there is a combination of fundamental and first overtone models with the fundamentalization of first overtone models. And you can see that there is a clear evidence of a metallicity effect. Obviously, for RLR, the period luminosity relation only exists in the near infrared bands. So these relations are represented from the R band to the K band, from top to bottom. And in the right plot, you have instead the mid-infrared filters. These are the model transformed also in the mid-infrared filters. This means that you can derive period magnitude metallicity relations because the slope is insensitive to metallicity, it's a matter of 0 point. So you can derive period magnitude metallicity relation for all these filters. And if the distances are known or your sample is composed of RLR that are all at the same distance, this relation can be inverted to infer some indication on the metallicity distribution. This approach has been followed by Vittorio Braga and co-workers in this paper of 2016 for Omega Centauri. Indeed, we inverted our predicted period magnitude metallicity relation in the I band and inferred that the metallicity distribution of RLR represented by the black histogram in this plot that is compared with the literature metallicity determination that is represented by the red one. So there is a good agreement, but this just shows a possible application of these theoretical metal-dependent relations. As for the helium abundance, it is interesting to note that concerning the instability strip, these are again the extreme boundary of the instability strip, so the first overtone blue edge and the fundamental red edge represented for different combination of metallicity and helium abundance, and the metallicity increases toward the right and the helium abundance increases from bottom to the top panels. And we see that the width remain more or less the same. The main effect of variation in the chemical composition is related to the different luminosity level of models that are pulsating within the strip. And this reflects also in the predicted period luminosity relations. Here are again from R to K, so the wavelength increases from from top to bottom, and the metallicity increases from left to right. You see the distribution of models in the period luminosity planes. And you see that increase in the helium abundance from the standard helium abundance that is represented by black symbols to 0.30 pink symbols and 0.40 blue symbols. There is an increase both in the luminosity, in the brightness, and in the period, with an effect that is not as evident as expected because there is a parallel combined increase of period and luminosity. Anyway, if we perform a regression, we find that there is also an helium abundance term to be taken into account. And this effect is not as high as the metallicity effect, at least for the period luminosity relation. When instead you move to the other fundamental relation that is used as for RLR when they are considered as standard candles, that is the absolute visual magnitude versus metallicity relations, we find that both in the V band, that is the bottom panel, and in the B band, that is the top panels, models for different helium abundances show significantly a much higher dispersion when the helium variation is included. And this means that this relation is significantly dependent on the helium abundance due to the increase, again, of the luminosity of the zero-age horizontal branch phase. And in this case, you do not have the period in the horizontal axis, but the metallicity, so the effect is higher. We transformed the theoretical scenario into the Gaia filters as well, in order to test some of the prediction against Gaia results. In particular, we transformed into the GWP and GRP filters. So these are some light curves on the left and the representation of the Bailey diagram for the three filters for 3 different metallicities that are the 3 different colors for zero-age horizontal branch models, so the lowest masses and the lowest luminosity, and the evolved models represented with the dotted lines. And you see that there is an effect as expected both on the period range and in the amplitude of the evolutionary effect of our evolutionary phase of our outlier stars, as well as an effect of the assumed metal abundance. This is a behavior that was already found in optical bands in other photometric systems, obviously. Here is the period Vasenat relation. We cannot derive period luminosity relation here because these are optical bands, but we can derive the period Vasenat relations in these bands. And again, we obtained the relation for fundamental first overtone, the global one that include the fundamental and fundamentalized first overtone models. The metallicity produces fainter relation, as already found. So the effect of metallicity is to make the relation fainter. But again, the slope remains the same. So it is possible to derive period Mannich, period Vasenite metallicity relations. This is the same plot, but including the helium-enriched models. So overimposed, you have the 0.30 and 0.40 abundances. And you see that, again, the slope remains more or less the same, and the effect is mainly a shift toward brighter luminosity, brighter Vasenite functions and longer periods. We decided to apply these period Vasenite metallicity relations. We assumed the standard helium abundance and used the period Vasenite metallicity relations to derive individual distances for outlier in the Gaia releases. We performed the first test with DR2 and then with EDR3. And indeed, by applying these relations to the Gaia photometry, assuming some spectroscopic metallicity information, complementary spectroscopic metallicity information, we could derive individual distances and in turn individual parallaxes to be compared with Gaia results. This was the... Sorry?
3
okay.
minutes left.
Thank you. This is the first comparison with DR2 Gaia parallaxes, and the metallicity were taken by Magurno et al. Compilations with some addition from the literature. And these are the differences between Gaia and predicted parallaxes. So they are really quite small. Here the Lindgren correction was also applied. The Lindgren correction to the parallax offset 0 point. And this is instead with EDR3 also, and using Magurno et al. Complemented with Crestani et al. Spectroscopic metallicities. Here Lindgren parallax was applied, and then we counter-corrected by Ries et al. Offset, who stated that probably the Lindgren correction was too much. And we find that the agreement is quite good. There is an evidence of a slight trend we are now investigating because it's not clear, at least for first overtone RRI. We also transformed the scenario in the Rubin LSST filter in the context of our activity in the transient and variable stars scientific collaboration. And again, we produced atlas of light curves and a Bailey diagram for both ZAB and evolved models. And here an interesting result was about color-color relations. We performed these plots assuming different pairs of colors. And we find, for example, that the highest metallicity effect is found for G minus R as a function of U minus G. And there is a residual dispersion within each sequence, each metallicity, that could be due to gravity variations, but we have to look at it in more detail. And this is the plot that represents I minus Z as a function of R minus I, the least metallicity effect. And this is an interesting linear behavior between R minus I as a function of G minus R that allowed us to derive some regressions of G minus R as a function of R minus I and metallicity, but also the metallicity as a function of the two colors. And finally, we also produced the theoretical pyroluminosity relations in the Rubin LSST filters in the near-infrared range. And again, we're able to derive the relations for fundamental first overton and combined modes. And also period Weisenheit relations. And again, we found that there is some combination of filters where the period Weisenheit relation is predicted not to depend on metallicity. The metallicity effect is really very small. So we are still, this is some results that they are still studying in more detail in order to understand we can find other useful combination of filters to infer as much other parameters that can be interesting to determine. And so it's time for my conclusion. I recently developed a theoretical scenario that spanned a wide range of parameters, has been transformed into a variety of filters, and the results are essentially here. There is a period Weisenheit relation in the BV bands that is predicted to be essentially metal insensitive. As for the near-infrared pyroluminosity relations, they depend on metallicity, and their inversion can in principle provide useful information on the distribution of metallicity of the host systems. Helium abundance variation produce brighter pulsators, and there is an effect that is in particular important for the optical magnitude versus metallicity relation. We applied the period Weisenheit metallicity relation derived in the Gaia filters to RR in the Gaia database with spectroscopic metallicities and found individual parallaxes in agreement with Gaia. And we are now working on the theoretical scenario transformed into the Rubin LSST filters to derive information, for example, from the predicted color diagrams that are found in for some filter combination to depend linearly on metallicity, and also the results for the period Weisenheit metallicity relations. Thank you for your attention.
Thank you, Marcella. Great. Questions for Marcella? Barry.
It seems a little bit counterintuitive that the near infrared should be more sensitive to metallicity where there are fewer lines than in the optical. Would you mind elaborating on that a bit?
Yes, you are right. Indeed, the metallicity term of the absolute visual magnitude, the metallicity relation is not much higher than what we find for the metallicity coefficient of near-infrared relations, but the difference is that the coefficient of the period is the same, so it's only a matter of 0 point, and indeed it is even the large range of metallicity we are exploring that probably produce this effect. If you perform the same kind of analysis on a restricted metallicity range, you find a smaller coefficient. So we are made some simulations in this sense.
And if you had, only a choice of only 2 or 3 filters to estimate metallicity and helium, which ones are the best and most informative?
For the metallicity term, I think the period I band magnitude metallicity relation is a good indicator. As for the helium abundance, it's not so easy because there is not, yes, you can include the linear term with the helium abundance in your relations, and maybe you can use other relations in other near-infrared filters. So maybe K and I could be useful if you only use pyroluminosity relations.
Great. Looks like there is no more questions. So last call. Okay, if not, let's thank Marcella again.
Thank you. Thank you again.
Okay, And our